Now that we have a Boolean algebraic format to represent this function block diagram, we will go into representing the function block diagram in a circuit diagram format, something like this. If you want to know how we came about this, please click on the link below and it will take you to the video. So, but before we go into that, we want to understand other function block variations. Now, there is this other function block called NAND, and there is also NOR, and then negative AND, then negative OR. Now we need to understand what all this function block means. This will help us to answer this question better. So a NAND in function block diagram look like this. This is a NAND, and let's assume we have an input A and B here. This is what we call a NAND. If you notice, we have something similar here. And then a NOR looks like this. An OR function block, but also with a not sign. So which means not OR. And that not means that we are inverting the output of the operation between these inputs. A negative OR looks like this, same as negative AND, almost same as this, but then the output, the input is knotted, and this is a negative AND. Whereas a negative OR would look like this, with an OR sign inside of it and then an output. So these are ways we represent this in function block diagram, and they also have their representation in Boolean expression. Say for instance, this would look like this: A dot, which is the AND, B OR bar. This would look like A plus B OR bar, and that's because the output here is bad. Remember what we did here, all the output, everything here is bad because of this output. So and then a negative OR will look like this: the input has its own bar, and then dot output have its own bar. Let's assume we have A and B here as well. Same applies here. So this is a negative AND, and a negative OR will be A bar, then plus B bar. Now, understanding this will greatly help us to solve this question. So this means that A and B, the output is all bad. So which means whatever comes out of here is bad, and that's why we have this. Same applies for OR. And this means the input of A and B are individually bad, which is negated, and then it doesn't affect the output because it's not bar, and that's why we don't use this. Then we have A and B here, input all bad, and then no output bar. So this is Boolean expression and function block diagram representation of this. Now let's talk about De Morgan's theorem. Let's talk about De Morgan's theorem. De Morgan's theorem. De Morgan's theorem shows how these function block diagrams, or Boolean algebra as the case may be, how they relate with each other, the similarities between them. De Morgan, who all happens to know George Boole, the man who discovered Boolean expression, proposed that A dot B or bar is the same, or at least have the same output as A plus B, now with each of them barred. In other words, if the output here is V, then it means the output here is also V, because this represents this and this represents this. And we are saying if the output here is let's say Q, and then the output here is also Q. So that's what De Morgan says, and it then means same applies that A plus B or bar is the same as A bar dot B bar. Notice that the sign here changes. The sign that joins them together when they shared the same bar changes to plus, as in this case it's a dot sign, and then each of them have its own individual bar. It's like saying, hey, we live in the same apartment, hey, let's all move out to a separate apartment, and then we can relate to each other not as brothers anymore, but as friends. So now they live in the same apartment as brothers, but now moved out to live in different apartments and kind of relate as friends. Or you can choose to treat the behavior as you wish, but that's something to explain what this is about, at least to give you an idea of what it is. So having known this now, so this is De Morgan's theorem. So why do we need to know De Morgan's theorem? This will help us to understand how to relate these function block diagrams and how to break these long chain of expression into a smaller unit that will look a lot more like this, with each of these elements sharing their own bars. So in other words, 5 brothers moving out from one apartment, or to live in their separate apartment and then relate in different ways. So now this is how we can show that expression. S1 dot S2 and dot S3. Now I'm trying to repeat what we have here. Or bracket S4 plus S5 equals V. So, and then we have this all bad. So we have to use De Morgan's theorem to break this down into smaller units. Now, if we notice, we can represent S1, S2, and S3 with A, and then S4 plus S5 with B. In other words, all the elements that are connected through a product sign will be represented as A, and the ones connected via a plus sign will be represented as B. And so we have, and looking at that, it means that we can find a similar equivalent representation for it. So which means all the A's will have its own bar and all the B have its own bar. That is S1 dot S2 dot S3 we have its own bar. Now let's not forget that the bracket here represents that there is a multiplication sign here, as in mathematics. So everything here is multiplying the sum of these two. So we have, and that means it's going to change to plus. So the dot sign here, or assumed dot sign here, is going to change to plus. And then we have S4 and S5 we represent as B. We become S4 plus S5. Now we keep this plus because the operation is acting only on this for now. That's why all of this will share one bar, equals V. Now, De Morgan's principle still applies because we have not yet broken these bars into individual elements. We've gone thus far to break it to 2 bars, but we need to break it to 5 different bars so that each element shares its own bar. In other words, all the elements moved out to their own separate apartments. Now, it then means that the operation that connects these two will further break to become plus. That means S1 now has its own bar, then plus, the sign changes to S2 with its own bar, plus S3, separate bar. Now, because there is no bar covering this, so it doesn't affect the plus sign, so the plus sign stays. But then we move to the ones that have the bars covering them. It means S4 dot S5 equals V. So now, and yes, there is the bar, of course, on it. Now we have these, and we have been able to break this into each individuals having its own, bars. And then we can rewrite this as S4 mathematically, S5 bracket, multiplying this S1 bar, all bar, of course, and then plus S2 bar, then plus S3 bar. Now, we have a more simpler and easy to work with expression for that equation or expression we have here. Now, the reason why we need this is because it's a lot simpler to show a circuit diagram knowing that as all the elements have a way we can represent them in the circuit diagram. If you recall the last time we said that each element shows whether it is a normally closed or a normally open function. In this case, switches rather. In this case now we know that they are all normally closed switches. So that's how we have to represent this in a normally closed format. So which means we have S4, which happens to be a normally closed switch, in series dot, remember from the first video, that in series with S5, which is also a normally closed contact. Now, then we go ahead to show, let's not also forget that we have a plus sign here. So plus, which means is in parallel with the whole of this, and the whole of these are all in series with each other or in parallel with each other. So the output of this S4 and S5 is in parallel with S1 normally closed, also in parallel with S2 normally closed, and S3 normally closed. So we have here S4, S5, S1, S2, and S3. So if you remember in mathematics, the output of all this is multiplying with a 1 here, which we don't show usually. So this now is the function, the circuit diagram that represents this Boolean expression. We can say that the output here is connected to an output, or the whole of this is connected to an output V, and that's here, V. And so we have a circuit diagram that represents the Boolean expression, and also as the function block diagram we have here. This is the answer to this question. Thank you for watching, and hope to see you in the upcoming videos.